Yeah, good morning. Greetings to all. So, in the last class, we have discussed the system, change of a system, path, process, cycle. After then, in depth, we have gone into the process, that is a reversible process and irreversible process. So, once again, recapitulating the contents in last class contents. So the reversible process is nothing but it is a process in which the system and all parts of the surroundings can be exactly restored to their initial states after the process has occurred. So that is known as the reversible process. Example, already I told you that the household refrigerator and steam thermal power plants where properties will come back to the initial states. So that is nothing but reversible process. So in a reversible process, already we have discussed that it is a constant pressure process, constant volume process, isothermal process, adiabatic process, iso isentropic process, polytropic process. So all the process that is in a reversible process, all the process which we will represent in terms of a continuous line, which we will represent in terms of a continuous line. So that you can also call it as a quasi-static process. Some of the examples are already we have discussed related to the reversible process, that is motion without the friction, restrained and controlled compression and expansion of the process, isothermal and frictionless adiabatic process. Next one is the elastic stretching of a solid. Here, the restrained discharge of a battery and electric circuit with zero resistance. So these are the examples that we have considered. These are the examples that we have considered. Next one is we have discussed the irreversible process. So in an irreversible process is called irreversible if the system and all parts of a surroundings, if the system and all parts of a surroundings cannot be exactly restored to their respective initial states after the process has occurred, right? Hope it is clear. So in this particular case, the irreversible process, so that is the irreversible process can be represented as a dotted line. So this is the dotted line with the direction that is 1 to 2, dotted line, and this we can also call it as a non-quasi-static process. This we can also call it as a non-quasi-static process. Next one is in a irreversible process, there are two varieties are going to exist. That is, internal irreversibilities are there and external irreversibilities. And what are the examples connected to the irreversibility? So that is the heat transfer. How this is going to occur. That is heat transfer through a finite temperature difference. So heat transfer through a finite difference in temperature, we will consider it as a irreversibility. Here, unrestrained, observe this one, unrestrained expansion of a gas or liquid to a lower pressure. Spontaneous chemical reaction, that is also the irreversible process, right? But here, the electric current flow through a resistance, that is nothing but irreversible, right? So these are the things what we have discussed in the last class. So at the end also we have touched upon the homogeneous system, heterogeneous system, what is meant by a phase and its example. So once again reminding that the phase is nothing but here phase there are more than one phase, single phase and more than one phase. So phase invariable chemical composition, invariable chemical composition. So the phase is defined as it is a homogeneous part of a system. Phase is defined as a homogeneous part of a system, homogeneous part of a system separated by a boundary surfaces having the same intensive properties, right? So homogeneous means it is having a single phase. Homogeneous means a system having a single phase is called homogeneous system. Say petrol engines, homogeneous mixture is entering, right? In diesel engines, heterogeneous mixture is entering. So In diesel, that means a diesel engine is nothing but one system consisting of more than one phase. So the heterogeneous part of a mixture is entering into the diesel engine. So apart from that one, the pure substance is also considered, right? So pure substance is nothing but is the substance which has invariable chemical composition in all the phases, which has invariable chemical composition in all the phases. So the examples for the pure substance is mixture of ammonia gas and ammonia liquid, steam and water and air, right? So these are the examples you have to consider. So the examples for homogeneous system, the ice, water, dry saturated steam, mixture of ammonia in water, water plus nitric acid. So these are the examples for homogeneous system. Examples for heterogeneous system is nothing but mixture of ice and water, water plus gasoline, and wet steam. So this is the heterogeneous system, right? So now we will move on to the next content, that is the fifth video lecture. So in the fifth video lecture, we are going to discuss the energy. So we are going to discuss the what is meant by energy. That is, we are going to discuss the energy in state and in transition, types of energy, heat and work, point and path function. So this is for today's class. This is for today's class, right? This is the content which we have to discuss, right? So now, what is the course outcome from this particular content? So the course outcome from this particular content is students are going to able to understand the types of energy and its transformations, heat and work interactions with the system, point and path function, point and path function. So how these are connected to the heat and work. So this is the outcome from this particular content. Now coming to the basic definition of a energy. So this energy, most of the times we have learned this particular content from lower school levels also, right? So once again, reminding the energy and its basic definition. So energy, it is defined as capacity to produce work, capacity to produce work. But however, the capacity has some physical significance. So what is that? It is a combination of effort and the change brought about by the effort. Combination of effort and the change brought about by the effort. However, the effort, the effort is nothing but it is exerted in overcoming resistance to a particular type of exchange. So normally energy cannot be seen, but its presence is indicated by the properties of a substance such as density, pressure, hotness, electrical resistance. So the energy we cannot see it with our eyes. So the effort involved is measured quantitatively. The effort involved is measured quantitatively, that it is nothing but in thermodynamics we will call it as a driving force, right? So in engineering mechanics also we will learn the work, and in thermodynamics also we will learn work. In electrical and electronics we will learn the work out, right? So the energy, so the different kinds of work. So this heat and work are nothing but the energy. So a driving force is nothing but it is a property which causes and controls the direction of a change in another property. This is very important. A driving force, which is a property which causes and controls the direction of a change in another property. So the quantitative value of this change is called the displacement. Is called the displacement. So the product of driving force and its associated displacement represents the quantity of energy. Represents the quantity of energy. Product of driving force and its associated displacement represents the quantity of energy. But in thermodynamics, this quantity has a meaning only in relation to a specifically defined system. So most of the times this energy and mass are equivalent and they are also mutually convertible. But in thermodynamics, the change in mass being very small it is assumed to be conserved. But in nuclear reactions, the change in mass is quite considerable, and we have to consider the change in mass in thermodynamic calculation. So now this energy, and energy can be classified as a microscopic energy and macroscopic energy. So the macroscopic energy is nothing but it is the energy as a whole with respect to some outside reference point or some surroundings, outside surroundings, and the change in velocity and elevation to a reference. So example, the kinetic energy and potential energy, we will consider it as a macroscopic energy. Now coming to the microscopic energy. So this microscopic energy is nothing but energy associated at the molecular and at the atomic structure level. So this energy related to the molecular structure and the degree of molecular activity. So the microscopic energy can be classified as a sensible energy, latent energy, chemical energy, and atomic energy. In general, the sensible energy, this we can consider it as a sum of the translational energy, rotational energy, vibrational energy, electronic energy, right? So the spin energy. So these are all nothing but the sensible energy. Next, latent energy. The energy associated at the intermolecular, that means a phase change process, a phase change. So that you can consider it as a latent energy. Chemical energy, the energy associated with the atomic bonds. So that is nothing but chemical energy. Next, the atomic, the energy associated at the bonds within the nucleus of the atoms. So this is nothing but these are all the microscopic forms of energy. Whereas the macroscopic forms of energy is nothing but only the kinetic and potential energies. So the energy can exist in numerous forms. Energy can exist in numerous forms such as thermal energy, mechanical energy, kinetic energy, potential energy, electric energy, magnetic energy, chemical energy, nuclear energy, and their total sum you can call it as a total energy of the system. So this thermodynamics deals only with the change of the total energy. So this is what you have to observe. So the macroscopic energy, that means those system possesses with respect to some outside reference frame, such as kinetic and potential energies. Whereas the microscopic forms of energy, those related to the molecular structure of the system and the degree of molecular activity. Internal energy. So the sum of all the microscopic energies, the sum of all the microscopic forms of energy, you can call it as a internal energy. You can call it as a internal energy. So now you observe the diagrammatic sketches here. So what are the diagrammatic sketches are there here? The molecular, so here the molecular translational, molecular rotation, see here the molecular rotations. Next, this one, this is consisting of the sensible and the latent energy, and electron translation, molecular vibration. So the energy involved the atomic bonds. So that is the chemical energy, electron spin, nuclear spin. So these are all nothing but the different kinds of microscopic energy. So the sensible energy, the portion of the internal energy of a system associated with the kinetic energies of the molecules. Portion of internal energy of a system associated with the kinetic energies of molecules. Whereas the latent energy is nothing but it is the internal energy associated with the phase change of a system. Chemical energy, internal energy associated with the atomic bonds in a molecule. Nuclear energy, so the tremendous amount of energy associated with the strong bonds within the nucleus of the atom. So this thermal energy is nothing but sum of the sensible energy and latent energy, whereas the internal energy is nothing but the sum of the sensible energy, latent energy, chemical energy, and nuclear energies. So the internal energy of a system is sum of all the forms of a microscopic energies. Sum of all the forms of a microscopic energies. So you can also have in-depth knowledge onto this particular type of a microscopic study. So here there is a diagrammatic sketch. See here, if you take one substance or matter, so within this one, the random thermal motion of the molecules you can find. So the macroscopic point of view, the elevation level, some outside. So this is the reference framework, reference point, right? So the macroscopic energy, and this is the microscopic. This is the microscopic energy. So the macroscopic energy and microscopic. So this is all the microscopic energy. So the microscopic energy mode, it refers to the energy stored in the molecular and atomic structure of the system. It refers to the energy stored in the molecular and atomic structure of the system, which is called the molecular internal energy, or simply we can also call it as a internal energy. Internal energy. So that internal energy is denoted by capital U. So we cannot get the exact value of the internal energy. Only we can get the change in internal energy. So matter is composed of molecules. Matter is composed of molecules. So the molecules are in random thermal motion for a gas with an average velocity v, constantly colliding with one another within the walls. See, observe, constantly colliding with one another within the walls. Right? So that which is shown in the diagrammatic sketch, it is 4.6. So due to a collision, the molecules may be subjected to the rotation as well as vibration. So they can have the translational energy, kinetic energy, rotational, vibrational, electronic energy, right, chemical energy, or the nuclear energy. So these are all shown in the figure 4.7. So this is the in-depth knowledge of the microscopic energy, microscopic energy. So these are the various formulas related to the kinetic energy, half mv square. So these things you have learned at the lower level. So kinetic energy half mv square, potential energy mgz, right? Say suppose if you want to express that in terms of kilojoule per kg, the kinetic energy is nothing but v square by 2. So this is nothing but the internal, the intensive property. This is nothing but the intensive property, right? Next, potential energy, kilojoule per kg. So overall, the energy is nothing but internal energy, kinetic energy, and potential energy. So these are the things which you can consider. So energy of a system per unit mass, it is represented as a small u, that is a small kinetic energy, small potential energy, u plus v square by 2 plus gz. That means now per unit mass you have to represent. So small e is equal to capital E by small m, that is mass of the system, right? So that is all about the uh, different energies. So in this case, the total energy, so already we have studied the different energy contents. So the total energy of a system, this can be contained or stored in a system. Total energy of a system, this can be contained or stored in a system. Thus it can be viewed as a static forms of energy. It can be viewed as a static forms of energy. So the forms of energy not stored in a system, the forms of energy not stored in a system, this can be viewed as a dynamic forms of energy or energy interaction. Now you have got the difference, basic difference between the static form of energy and dynamic form of energy. So the dynamic forms of energy are recognized at the system boundary as they crosses it, and they represent the energy gained or lost by the system during the process. So only the energy interaction, that means there are two forms of energy interactions associated with a system are heat and work. So the difference between heat and work, that means if an energy interaction is the heat transfer, if its a driving force is a temperature difference, then we can consider it as a heat. Otherwise, we will consider it as a work energy. Otherwise, we will consider it as a work energy. Now you can observe the hydraulic energy, how this hydraulic energy. So in this case, you can clearly identify the macroscopic energy and microscopic energy. So the microscopic kinetic energy of the molecules, this does not turn the wheel. The macroscopic kinetic energy, which is going to turn the wheel. So the macroscopic kinetic energy is an organized form of energy and is much more useful than the disorganized microscopic kinetic energies of the molecules. So this is what you should have to know more about the energy. Now the next content what we are going to discuss, what is the basic difference between energy in storage and energy in transit. Energy in storage and in energy in transit. So the energy in store. So now you observe energy in storage. The symbol E refers to the total energy stored in a system. Basically, there are two modes of energy which may be stored. That is the macroscopic energy mode and microscopic energy mode. So the macroscopic energy mode includes the macroscopic kinetic energy and potential energy of the system, right? So if you just observe that, let us consider a fluid element having a mass m with a center of mass velocity v. The macroscopic, the macroscopic kinetic energy of the fluid element by virtue of its motion is given by Ek is equal to half mv square. If the elevation of the fluid element from an arbitrary datum is z, then the macroscopic potential energy is mgz. Then what is meant by energy in transit? So transit, it is a transient phenomena. Energy that is transferred to or from the system. Energy which is transferred to or energy which is transferred from the system is called energy in transit. Energy can be transferred only when a driving force or potential is existing. That means change in temperature or temperature gradient. When this is existed, energy can be transferred, right? So in general, energy is transferred in two forms, that is the work and heat. Thus, energy in transit may be classified as into heat and work. So the work may be the mechanical work or the electrical work that you should have to understand. Next, some of the examples, when we discuss the heat and work in this particular case, normally the heat is defined as a form of energy. Heat is defined as a form of energy, or you can call it as a thermal energy, that is transferred by virtue of a temperature difference or temperature gradient. So, body never contains a heat, but that heat is identified when it crosses the system boundary. Example, say suppose if you take the hot block of a copper, when it is dropped into a beaker of cold water, heat lost by the copper block is equal to heat gained by the cold water. So this is what the meaning of heat. Heat is a path function. The amount of heat transferred, heat is a path function. So there are two points which you are going to get, point function, path function, which you are going to get in the next stage. But before that one, the heat which is going to come onto the path function. So heat is a path function. Work is also the path function. The amount of heat transferred when a system changes from state 1 to the state 2 depends on the intermediate state changes when a system passes. Hence, heat is an inexact differential. So, the heat and work are represented as in terms of this d bar q or d bar w, inexact differential, right? So that things you have to observe for this heat, right? Next, the work. So what is meant by work? So the work is nothing but work is done by a force as it acts upon a body, as it acts upon a body moving in the direction of the force. Work is done by a force as it acts upon a body moving in the direction of a force. So the action of a force through a distance is called the mechanical work. Since other forms of a work can be identified, but we will discuss in the next stages. So the product of the force and the distance moved parallel to it is called the mechanical work. So in engineering mechanics, where you are going to learn the mechanical work. Whereas in thermodynamics, this work is equal to pressure into change in volume. So that we can call it as a work. So in thermodynamics, work transfer is considered as occurring between the system and the surroundings. So this work is said to be done by a system, or work is said to be done onto the system. right? So suppose if you see the two examples here, the battery motor system driving a force. So here work, some work is given to running of the fan. So from the system to the surroundings, but the work transfer from the system. So the same battery motor, and now here, the rising the weight up and down, rising or lowering the weight up and down. That means here work is doing onto the system. So this is work done by system, work doing onto the system. So there are two things that you have to observe while discussing the heat. When heat is entering into the system, it is a positive. When heat is leaving from the system, it is negative. So in the same way, in case of a system, work doing onto the system, it is negative. Next, in case of a system, work done by system, it is positive. Work done by system, it is positive. So these are the two things that you have to observe while studying or while solving the problems. While solving the problem. So this heat and work is over. There are some examples related to that one. The tire, the air in a tire and connected pump. The pump forces the air into the tire. Assume tire and pump and connecting tube to be non-conducting. Non-conducting means heat transfer is zero. So the heat transfer is zero, right? So the water and water vapor in a rigid metallic container. So the rigid, when we call it as a rigid, it is a constant volume. So the work done is zero, right? So rigid metallic container. The container is placed on a stove. The pressure and temperature of its content rise, right? So here, you are giving the heat input. So that's why it is a positive sign for the work. So like that one, some of the examples are also provided over here. Now, there should be some distinction. What is the qualitative distinction between heat and work? Qualitative distinction between the heat and work. So, in this case, now you have to observe. So, at what situation work is equal to heat, or heat is equal to work, or in what situation the heat transfer is more than the work transfer, or in what situation the work transfer is more than the heat transfer. So that is what you have to add. That means heat is a low grade energy, work is a high grade energy, and this work is a orderly form of energy where you can convert all the work into the heat. But in case of a low grade energy, you cannot convert all the low grade energy into the equivalent quantity or the equivalent amount of a work. So this is what the qualitative distinction between the heat and work. You can also go through this particular case. So finally, this here there is a diagrammatic sketch is there. So the Q1, that is the Q1 heat is leaving. So that's why it is minus sign. Q2 heat is entering. Q3 heat is entering. That's why it is a positive sign. So internally there is a system change, whether it is the internal energy, that is kinetic energy or potential energy. Next, work, the W work doing onto the system, that is minus. W4 work given to the system, minus 4. W3 work done by the system. W2 work done by the system. So this is the distinction that you have to observe for this particular case. Next, the importance, the difference between the work and heat, that one thing you have to identify. So what is that particular basic difference? The area involved onto the PV diagram, area involved onto the PV, that is, this is the pressure and this is the volume. So from this case where you can get the work transfer. So the area involved. So this is going to give the work transfer, whether it is for a closed system or open system, that we will discuss. Next, the heat transfer. So the area involved within this one. So the temperature on y-axis, entropy, that is S, onto the x-axis. So the area involved within this one, this is going to give the heat transfer. This is going to give the heat transfer. So the representation of a work transfer and heat transfer in a quasi-static process on a PV and TS coordinates, that is the temperature versus entropy. So from the TS diagram, you can get the amount of a heat transfer. From the PV diagram, where you can get the amount of a work transfer, whether that work is a positive or that work is a negative one. So the some of the differences you should have to know. What is the basic difference between the heat transfer and work transfer? You can go through this particular thing where you can get the much knowledge onto this particular the difference between the heat and work. So the last one is the point function and the path function. So when two properties, the path function, when two properties locate at a point on the graph, that is the coordinate axis, x coordinate, y coordinate, then those properties are called as a point function. Example, pressure, temperature, volume. So when you are going to represent that, when you draw the PV diagram, so onto the PV diagram, when you draw the PV diagram, this is 1 and 2. So V1 and V2 or P1 and P2 or T1 and T2. So these are nothing but the point function. There are certain quantities which cannot be located on a graph by a point, but are given by the area. So on that graph, in that case, the area on the graph pertaining to the process is a function of the path of the process. Such quantities are called as a path function. Examples are heat and work. So these heat and work are inexact differential, and this depends on to the path of the system. Their change cannot be written as the difference between their end states. So that's why you will represent that heat and work are nothing but inexact differential. So this d bar w or d bar q. Whereas in this case, directly you can write the change in internal energy or the change in volume or the change in enthalpy or the change in entropy or the change in volume, right? So these are nothing but the point function. So this is all about the point and path function. You can also go through that one, the question which is going to appear as a distinguish between the path and point functions with example. So this is all about the today's